All right. So next up, we have two master's students from, and I know Kwong's going to laugh at me because every time I have to say the Loyola University of Chicago, I screw up the name every time. The Zach Culp and Josie Peterburs. Zach is finishing up his MS in Applied Statistics at Loyola. Soccer experience, 3 years of playing soccer. So if someone finishing up, folks in industry looking to hire. And Josie is she's a graduate student, MS in data science at Loyola. And she is currently assistant operations manager for Loyola women's basketball team. I gotta stop trying to say it. I'm just giving up. So let me get the slides set up here and we'll turn it over to them.
Okay, hi everyone, I'm Josie and this is Zach, and today we'll be looking at assessing ranking fidelity of competition structures via weighted mutual information. So we're gonna start with a trivial example of a tournament. Imagine like a 4-team single elimination basketball tournament. Our 1 seed is the 2024 USA men's team in the Paris Olympics. Our 4 seed is a team of 5 babies. This is a real picture, by the way, it's not AI. Our 3 seed is a team of middle school girls, and our 2 seed is a team of 40-year-old men who play in a rec league together. So let's say we structured this in a normal way, with the 1 plays a 4, the 2 plays a 3. The tournament would look like this, but there are other ways we could structure this tournament as well. One other way, which wouldn't be as good, is the dream team plays the work group and the middle schoolers play the babies. So in our case, the dream team is never gonna lose and the babies are never gonna win no matter who they play. And then if the work group and the middle schoolers play each other, the work group's gonna win 95% of the time. So whichever tournament structure we use, we can get different outcomes, and we call this outcome of the rankings our rank hat or R hat, and we wanna look at the distribution of these rank hats. So let's say we want to award a gold and silver medal, we wanna correctly rank the top 2 teams. With the good tournament, we can do that 95% of the time because the dream team will always make it to the semifinals and the work group will win 95% of the time. And then the dream team will win the whole thing, so we'll get 1-2. And then we'll get 1-3, 5% of the time if the middle schoolers beat the work group. But for the bad tournament, since the 1 seed plays the 2 seed in the first round and the dream team is never gonna lose to them, those 2 ranks can never be 1-2 in the finals ever. So it's not as good as a tournament. We'll always get 1-3 as our top 2 teams. So for us, we want to determine which competition structure is best. But first, we have to consider what is best in our case. For us, a good tournament is where the top K teams produced by the tournament matches closely to the true top K teams. So in established literature, there are 2 main ways to look at this. One is effectivity, where you're interested in correctly ranking the best team as first. And there's efficacy, where the final ranking should match the true rankings of all of the competitors. So here's that visualized. An example of effectivity, where you care about getting the top team first, is the NCAA tournament. We're giving the trophy to 1 winner. An example of efficacy, where we care about ranking all of the teams, is the English Premier League. Because of relegation, we want a full ranking of all the teams. What we're interested in is the numbers in between. If we care about correctly ranking the top 3 teams, like in the Olympics, the gold, silver, and bronze medals, how can we make sure we get that ranking correct? Or for the NFL playoffs, each conference has the top 7 teams. For the Champions League, we care about the top 24 teams advancing. We call this number salient ranks, which we define as the output ranks of a tournament that we want to get correct. So 2 special cases I've already talked about. Effectivity, 1 is the only salient rank, and efficacy, and 1 through n are all salient ranks, so k would equal n. So our goal is to quantify how well a structure can accurately order the competitors using weighted mutual information. To do this, we propose a metric that quantifies how effectively different tournament structures recover the true ranking of the teams.
Okay, so like we said, we're using mutual information. So what is that? So think of mutual information. So you have your X, which is a message. In our case specifically, it's our true ranks of the team. So you have this message and you transmit it through a tournament structure. And the outcome is this R hat, which is just the outcome of a single tournament, and we have this distribution. So we want to measure the goodness of how well it's measuring that transmission and how much information is gained through the tournament. So in order to do this, we have the basic formula up there. And then in our case, it's simplified because the true ranks we are assuming are constant. They don't change. So it can be simplified to this formula below. So a limitation, though, of this is that it doesn't care about the direction of the information. So if you have equal probabilities of getting it completely correct in the ordering or completely incorrect with 4, 3, 2, 1, it will end up giving you the same score. So in order to combat this, we propose adding a weighting function to this. So that's what's in the box there. And then finally, we decide to normalize the metric by dividing by entropy. And this just makes it so it's a scale from 0 to 1. So initially in our paper, we use squared error loss as our weighting function, but after feedback through the Connecticut Sports Analytics Symposium and feedback from the paper in this conference, we decided to pivot, and now we are using a weighted Kendall's. So the formula up there is the Wij is a n by n matrix, and it's basically associated with each team. So for the top K team, so for K equals 1, you associate the first ranked team with a 1, and the rest are zeros, and that's how this formula is used. So you can see we have 1, 2, 3, 4. If you're looking at the top 2 teams, that gives you a perfect score. So we want the highest weight to be the best tournament. On the other hand, 4, 3, 2, 1 is the opposite. You get 0, which means this weighting function does work. And if you look here, we get where it's 1 and 3 and 2 and 1 actually end up with the same score. And this is because it's only one spot away, even though for the 3 is in the top 2, and this one has the top 2. It's not in the correct order. But if you see for the top 3, you notice how it's 1, 3, 2, and that has the top 3 with only 1 in the incorrect spot, and 2, 1, 4, which is slightly worse. So you see the drop comparatively. So how do we do this? We use a simulation study. So we simulate every games using this formula up there, and we assigned a theta value, which is associated with the strengths. So in an example of one simulation of a single elimination structure, we have thetas here, which this is just a distribution on a normal scale. And then you have the true ranks, which are what's assumed. You have the R hat. So the R hat is the outcome. So you see for the 4th team, they ended up with an R hat of 1, which means they ended up winning this tournament. So you can see how it plays out, and then we tracked wins and losses just for potential further experiments in that. And then the last thing to notice is this round 1, because there's 4 teams that lose in round 1, and there's no direct like losers bracket, we can't tell exactly where these rank. So throughout the simulations, we randomly assign these ties, and over many, many simulations, it all evens out. So our results, we did a bunch of different simulations. So we have worst possible and best possible. Those are still 0 and 1. Those were just checked. So if the tournament we use 10,000 simulations. So 10,000 of completely correct, 10,000 completely wrong. We get 0s and 1s. This coin flip round robin is where every team plays every team once. And a coin flip, basically, we're assuming the theoretical, if every team had a 50-50 shot of winning, what would that look like? And that gives you a 0.25. So that is basically our baseline. If it's somehow worse than that, that means you are worse than randomly assigning teams. Not entirely sure how that would be possible, but that is the worst case scenario. And then we have coin flip single elimination. So still 50-50, but it's single elimination. And the reason why this is actually slightly higher is because you think the 1 seed plays the 8 seed in the first round. well, the 1 seed and the 8 seed cannot end up in the final. So there is some information to be gathered from that based on how the seeding is structured. Next, we have in pink here, bad seeding structure. So this is 1 plays 2 in the first round, 3 plays 4, and etc. So you can see it still does a decent job at getting the top team right comparatively. It's worse than the rest of them, but it's still doing better. But after that, it kind of flattens out. And this kind of just shows how the metric for the top K teams does in fact work. And then round robin with the normal distribution of strengths was much better than any of the other ones, which is interesting because it was worse when it was a 50-50 shot. And then we'll take a closer look at these groups of 4. So we have single elimination reseeded, and that is basically like the NFL playoffs. So for the playoffs, if the 1 seed, they get the bye in the first round, and the next round they play whoever the worst seed is. It's not a set structure, it's just best team plays worst team. So we have that. We have double elimination, which is where you have the losers bracket. You have single elimination with a set structure. This is like March Madness. And then group stage play, which is similar to the World Cup style tournaments. So an interesting thing to note is for the reseeded, you actually see there's a larger gap between where K equals 1 and 2 and 7 and 8 compared to like 4 through 6. And this is because when it's reseeded, it gives the probability that the top team wins is much higher because they are playing worse teams overall. Whereas in the middle, you're still playing what usually is expected to play. You're still playing the middle of the pack teams. And then finally, we originally hypothesized that the group stage would be much higher, closer to round robin. But after thinking about this, it's because there's variability in how the groups are played. So there's that variability, and then there's the knockout round. And in the knockout round, there's also variability. And if, say, for example, the top team ends up getting second place in their group, and the next best team is in the other group and gets first, those 2 teams then play in the knockout round, which would make these scores lower. So an overall summary is we use mutual information to analyze competition structures, and we want to find that from the range of efficacy to effectivity. And using this method, we didn't see anything out of the ordinary. We got the results we want, but we were able to get a value that can quantify the differences between these tournaments. So some limitations are we assume unknown ranks and we assign strengths. So for single elimination, as you saw with the bad seeding versus regular seeding, it can be very different based on how these are seeded. And in the real world, you don't know what the true strengths are, so it's harder to quantify that in the real world. And future works is we want to show how we saw where the 50-50 changed which one was better. So we want to look at the distribution of thetas and how that distribution can impact which tournament is actually better, and look at more tournaments.
And now we'll open up to questions.
All right, thank you. We have time for one question. You're making me go all the way in the back.
Thank you so much for your presentation. It was really good. One question that I had was, obviously, what we want to do at tournaments is try and get as much of this information as possible with as little fixtures as possible, because having a lot of fixtures will give you the information, but it will be like tolling on players, and it'll take a lot of time for that tournament to happen. So, like, with that in mind, like, were you like, what systems other than like these standard tournament designs did you use? And also, did you consider like the Swiss system that they use in chess and like esports when it comes to like this tournament style where teams with similar records end up playing each other?
Yeah, so we actually have a list of tournaments that we have not yet covered. This was just, we created the metric and just wanted to test the more well-known ones that we could tell what we believe order should be. But we did look, the Swiss is on our list to look at, and we want to look at a bunch of different ones that we see anywhere in the real world. And like, for example, the Champions League format just changed from that group stage to now it's like this large group play and it's the top 24 teams advance. We want to look at maybe how does that change influence. Another example would be the college football playoff expanding. How does that change influence how well a tournament does? So yeah, we will. That was a great question. We will look at more tournament structures in the future.
All right, let's thank our speakers for a great job. And now we are going to switch over here into our poster session.